Hello and welcome to another class on organic chemistry that's going on in class 12. The first program was haloalkanes and haloarenes, and we are doing now today haloarenes. So before coming, like chlorobenzene, like bromobenzene, like how can this be named? 1-bromo 3-methyl benzene, or you can fondly call it as metabromotoluene. If you make the parent compound as toluene, a derivative of toluene, you can say metabromo or toluene. But the IUPAC name will be 1-bromo 3-methyl benzene and so on. So before coming to discuss about the preparation of haloarenes and their properties, I would first discuss about the mechanisms. First, the one which Samidha you wanted, to start how chlorobenzene is prepared. This is the usual method of preparing chlorobenzene. There are many industrial method, commercial method, which we will discuss. But the simple laboratory method is electrophilic substitution. You take chlorine or bromine. If you take bromine, then you take ferric bromide or simply Fe with excess of chlorine or bromine. That will do the same job and we get chlorobenzene, or in general halobenzene. This X stands for Cl or Br. This method is not suitable to get fluorobenzene and iodobenzene. I'll tell you how fluorobenzene is obtained from the other track, from benzene diazonium chloride, as well as iodobenzene is prepared through BDC, benzene diazonium chloride, and also other method. We'll do that later. But this is ArSC. The mechanism that we studied and I would like to revise is ArSE, electrophilic substitution. And since it is common in benzene or aromatic compounds, often we call ArSC. Electrophilic substitution is not common in aliphatics. It is there, but it is uncommon. But it's very common in aromatics. There, what happens, as you know, the incoming group is electrophile. Benzene itself is a nucleophile, as it has a lot of electron cloud, homogeneous and uniform electron cloud above the ring and below the ring. So it acts as a nucleophile. So this can be Cl plus, this can be Br plus, this can be any E plus in general. And you know the leaving group here is S plus. Now, in this mechanism, if I remind you that you put any, like chloronium ion, which is obtained by the reaction of FeCl3 with chlorine, give you chloronium ion and FeCl4 minus. So this chloronium ion will attack in the slow and rate determining step to form an aranium ion, benzenonium ion, aranium ion in general. Supposing attaches here, anywhere, then this will be plus, and there is a hydrogen, already existing hydrogen, as in all carbon atoms. This is a resonance stabilized aranium ion, which we can show the other resonance structures. This is one, the other one is here, and the third one is here. So this is put a square bracket to show the three resonance structures of this arrhenium ion. I'm not going to write the details. I mean, arrhenium ion in language, you know this. This we have done in class 11 Arenes. And why I'm repeating, revising to distinguish between ARSE and ARSN. Here, we are preparing chlorobenzene from benzene. And then the second step, which is fast, this. Oh, I'm so sorry. Yeah, not sorry at all. And the second step, this proton elimination takes place. The proton is lost in the second step, which is very fast, and we get the aromatic structure, the stable aromatic structure with chlorine attached. H plus leaves. The leaving group is H plus. Therefore, the breaking of the CH bond does not contribute to the rate. If you take deuterated benzene and ordinary benzene, you don't find any difference in rate. Although CD bond is stronger than CH bond, many times stronger, still then you get the same AC rate. Because the rate determining controlling first step does not involve the breaking of the CH bond. Had this step would be slow, would have been slow, then definitely there would be a difference in the rate. When you take deuterated benzene, would have been slower. Therefore, we learned that Kh by Kd is equal to 1. Kh, the rest constant when all are hydrogen, ordinary benzene. Kd is a deuterated benzene. They react with the same rate for any electrophilic substitution, excepting sulfonation. I remind you that there is a little, this is called kinetic isotope effect, which is not found in ARSE usually. There is one exception. Sulfonation does show a slight kinetic isotope effect of 2. Because the deuterated benzene reacts 2 times slower than the ordinary benzene, showing that the second step also takes part in the rate law. This is not very fast. So it is not as much slow as this, but slow. So in the mechanistic rate law, both first and second steps they come, and therefore, since the second step KH bond is a CH bond is weaker than the CD bond, so the deuterated benzene reacts 2 times slower. Otherwise, there is no kinetic isotope. ARAC has usually no kinetic isotope effect. I'm writing this KIE. Now we'll be doing a little bit more on ARAC. The directing influence of host groups. Supposing another groups are there, when there is a plus R, as we sometimes call plus M groups, like OH, like NH2, like OR, there is a lone pair, like OCOR, acyloxy, OCOR. O is directly attached to benzene ring, or NHR, or NHR2. All these, NR2, NHR or NR2. These are plus the electron donating groups with resonance effect, right? So such groups are OP directors. They and activators, they not only directs the incoming electrophile to the ortho and para positions, but also it enhances the ARAC rate. The reason, once a group like OH is there, if you draw the resonance structures, the four resonance structures, I am avoiding here, you will find in the resonance hybrid, in the hybrid structure, you will be having minus delta, minus delta, minus delta at the ortho positions and para position. So the electrophile will prefer attacking to ortho and para positions. Since the probability factor of ortho is 2 times more than para, unless there is a steric effect, steric hindrance effect, ortho product should be more abundant major than the para. But sometimes the host group or the incoming electrophile, they are bulky or both are bulky. In that case, para is greater than ortho. The para is major, ortho is minor, despite its advantage of having the probability factor 2 compared to para 1. Because there are 2 ortho equivalent ortho positions. So there will be 2 times more probable having 1 ortho attack. We are getting 1 ortho, but there is probability factor of 2, so 2 times. Should be 2 times more. But that doesn't happen. When the groups are small, host and incoming, then there will be a definite preponderance, I mean, excess of ortho product than para product. But usually we get para product when the host group or the incoming electrophile, they are bulky. Steric crowding effect will not allow the electrophile to attack at the ortho position more, abundantly or more frequently. Now coming to minus, this is not only the plus R or plus M groups, and also the plus I, which has a plus H effect, the hyperconjugation effect. So these are also like alkyl group, these having at least one hydrogen atom. So that we are also orthopara directors, like methyl, ethyl, and other, even one hydrogen atom, if there is there, CHR2, or but CR3 is not that very prominent directive. That doesn't have a prominent directive effect, because one hydrogen is required at least, so that you can have the hyperconjugation effect, like the resonance effect too, so that the orthopara positions are relatively more electron rich and the attack to that positions will be preferable. Now coming to the second part is minus R or minus M, the electron withdrawing group through resonance, like NO2, nitro, like CN, like COOH, not like COOR. This is carboxy, alkoxycarbonyl. That was acyloxy. Here, there is no lone pair. There is a multiple bond heteroatom, so that will withdraw electron from the benzene ring. You have SO3H and so on. Aldehyde, ketone, all these are minus R groups. They are always meta directors and deactivators. They slow down the reaction, because if you draw, I'm not drawing now. Supposing you have nitro group. If you draw the resonance, 4 resonance structures and so on, you will find in the hybrid, these are the resonance structures, 4 resonance structures, and in the hybrid, this is a dirty bond plus minus. Okay, but here it will be reduced. Not sorry, it will be new partial charge minus delta will be created, and in the orthopara positions you will get plus delta. So when the electrophile will have to come it will not choose orthopara position because the meta position is comparatively more electron rich. But the ring has been, you know, electron deficient because the ring has been electron deficient because of minus R effect. So the reaction rate is slow. But if at all it has to attack, it will attack the meta. There are two equivalent meta positions. So, but there is no competitor like ortho and para. They come together. Plus delta, sorry, minus delta charge is created in all the three positions, two ortho and one meta. So the question of probability comes. Here there is only one meta, no competition with ortho and para. So you get only one product, meta product, NO2, and slow reaction. So here you get two products. Here, if you get this, you get a mixture of the OH is the host group. E will be here as well as here. You will be getting a mixture of ortho and para products. Which is dominant, which is minor, that will be decided by many factors like steric effect and other intramolecular hydrogen bonding effect, which might make the orthoisomer more abundant. We'll not go to that. Now, the third, I'll ask you the question from one of you about halogen, the chlorobromo, fluoro, iodo. Fluoro is little different. And these are interestingly OP directors, but deactivators. They have one quality of plus R groups like OP directors and the other quality of minus R groups, deactivators. Because for halogens, the dominant effect is minus I. Therefore, it withdraws the electron density and slows down the ARSC. But why then orthopara? It is because, as you have seen in the NCERT book, and we have also discussed, that when chlorine group is already there, we were studying chlorobenzene from benzene by ARSC. But here we will be preparing something chloro with another electrophile. So in that case, if E plus will attack, this is ortho or para attack. I am taking the ortho attack. If it attacks at the ortho position, then I am avoiding steps. I am avoiding steps ortho position here. Chlorine is the existing group. So this will have a plus charge. And similar manner you draw three resonance structures. But here, since there is a lone pair, there will be a p-pi back bonding. And this is a stable aranium carbocation or aranium ion. But in the meta attack, you will not find a plus charge coming to the ipso position with respect to chlorine. It will bypass to the other positions. So a stable aranium ion will not be produced while there is a meta attack. So meta attack doesn't happen. In some literature you will find, Shruti, Shreya, that for explaining orthopara orientation, you use plus R effect. There is a lone pair, you just write the resonance structures, you will find minus delta in the orthopara positions, hence it is OP director. And for deactivation, why it slows down, you say it has a minus I effect. I don't think this should be the explanation. If there is an electron going to the orthopara position by resonance plus R, then it should activate, it should enhance the rate. Why it is decreasing the rate? It is because it is the dominant effect is minus I. So once you are saying it is deactivating, minus I is superior to plus R, then how can you say the plus R effect is operating in the ring itself to make the orthopara positions electron rich so that the electrophile will attack to the orthopara? Now, so here you explain in a different way. You explain through attack mechanism. In the mechanism, In the first step, when arrhenium ion is formed, ortho and para also you will find the same position. You will, out of the three resonance structures, you will find one which is very stable because the plus charge comes adjacent to chlorine, bromine, which has a lone pair, and that small amount of p pi back bonding. This p orbital, which is parallel to this vacant orbital, they go for back bonding to stabilize. I used to say a localized back bonding. It's not a total ring delocalization, the lone pair entering into the ring. No. The intermediate arrhenium ion is stabilized due to p pi back bonding, back donation. That is why orthopara director. But since minus I is the dominant effect, it is deactivating. We are not writing down the details now because I will be jumping into ArSN. You remember all this, Samita? Now, do you have any
Yes.
question, Samita?
No, no, sir.
Shruti say,
No, sir.
who is saying? Who is saying no, sir? Shruti or
Yes, sir.
Shreya?
Sir,
Sir,
both.
both.
How to? Don't know. Very good. Very good. Okay. Now coming to, interestingly, ArSN. Here you have to write AR because SN is common in aliphatics also. That SN is completely different from ArSN. Aliphatic SN is simply said SN. So this ArSN has nothing common with SN1, SN2, SN1 dash, SN2 dash, SNI dash. No. In SN1, carbocation is formed. Here there is no carbocation formation. It's not SC. A negative ion is formed. And therefore, this is called addition followed by elimination kind of substitution. First, the nucleophile will be added up to form an intermediate. That is a carbanion. Arenide ion, that is arrhenium ion, this is arenide ion. And then in the second step, just like ARSC, the Liebig group here is Cl minus. There, the Liebig group was H plus. In every ARSC, usually the Liebig group is H plus. But there can be many other Liebig groups, but plus. But here, the Liebig group is Cl minus, Br minus. Just like in normal SN1, SN2, the Liebig group is Cl minus, Br minus. Here also, same thing. But it will happen in the second elimination state. So let me show you the mechanism here. Supposing you are carrying out a OH minus. So this will replace this. It's not like SN1 or SN2. It is completely different. And you will be getting OH and Cl minus. Now, the mechanism steps are totally different. The step 1, the benzene ring. No, I'm putting the double bonds in the reverse manner so that I will go clockwise. Now you will have to go for nucleophile. Nu minus, not E plus. You are doing nucleophilic substitution. So that will attack at the same position. See, it will attack here so that the pi bond will be polarized in the reverse direction. So you get a arenide ion. Here that was in electrophilic substitution, your He. He, whether it is simply benzene or some host group is there, doesn't matter. It will attack to a carbon, either orthopara or meta with respect to the host group, but the other partner with it will be hydrogen, which will leave in the second step. Here, the nucleophile will attack to the ipso carbon, the first carbon, in which chlorine is bonded. So there will be a negative charge here. This is the arenide ion. It's a carbanion. But it is resonance stabilized. Like aranium ion, this is also resonance stabilized, having three more, having two more, I'm sorry. This will come and this will come. So you write down the other resonance structure. So since the first step is low and the nucleophile is attacking, therefore it is nucleophilic substitution. But since it is different from the other nucleophilic substitution in aliphatic compounds, we always say aromatic nucleophilic substitution. And in the second step, which is passed, the leaving group goes. This comes here, aromatization happens, and the leaving group is chloride ion, goes, and nucleophile is permanently attached to the benzene ring. So this is, but there is a big but. I'm sorry. But it's not that simple. The question sometimes you are asked in NCRT, why SN reaction, that ArSN, is difficult in halobenzene. I explained to you only to explain the mechanism. I wrote the two steps, but it never ever happens. Why? It happens in a different condition, not the way I told. Why SN reaction is difficult in halobenzene? The reason answer that you give to get full mark is number one, draw the structure, a resonance structure of benzene with chlorine here, supposing here, this carbon is sp2 hybridized. Therefore, the CCl bond is stronger than in aliphatic compounds. This is sp3 hybridized, this is sp2 hybridized. So more percentage of S character will make the bond shorter and stronger. And moreover, CCl bond is stronger in chlorobenzene due to sp2 carbon than not writing than in alkyl halides where the carbon is sp3 hybridized. And number 2 point, benzene ring itself is a nucleophile. Because there is a lot of electron density. So which love electrophiles? They do not love nucleophiles. The benzene ring itself is a nucleophile. We are not doing, the resonance structure like that. We thought that we can explain ARAC, OP direction, OP directive influence of halobenzene through resonance plus R effect. So there is a minus delta, minus delta, minus delta. So the electrophile will attack in the orthopara position. So that we can't say. I have already ruled out because halo groups, they have predominant minus I effects. And here the leaving group is chloride ion, bromide ion, is not the H minus ion, hydride ion or something like that. It is the Cl and Br which is sitting will go as Cl minus Br minus. Situation is completely different. Therefore, it is very, very difficult. In fact, if I tell you chlorobenzene is subjected to KOH solution, alcoholic KOH, at say 300 degrees Celsius and at about 150 atmosphere pressure, external atmospheric pressure. Then you get no doubt phenol. You get phenol. On a very rigorous condition, vigorous conditions are used. But interestingly, the mechanism not ARSN. Although ironically, I explained you the mechanism through chlorobenzene and another nucleophile coming, expelling chloride ion in the second step. I explained to you. But the mechanism happening is something different. It is opposite. This is addition followed by elimination type of mechanism, which is called ARSN. But the opposite is elimination followed by addition type of mechanism. That is a different mechanism called the Cine substitution, CINE, not SINE, CINE, the name of a scientist. That happens, you get. But the thing is, it's not easy. It is difficult. Nucleophiles are not interested to enter. Who can tell me what change in the structure of chlorobenzene? You have to make a change. हमको ARSN करना है, लेकिन हम क्लोरोबेंजीन में नहीं कर पा रहे हैं क्योंकि there is no, because of sp2 hybridization, the CCl bond is strong. You can write down, hence the livability of Cl minus is poor because the bond is strong. Cl minus won't leave, and moreover benzene ring has enough electron density to hate nucleophiles, which is also negative or electron rich. So now tell me what modification in the structure of chlorobenzene you will make only to visualize ARSN. Yes? Any thinking?
Sir, can you repeat the question?
What structural change you will make in chlorobenzene so that ARSN will happen. ARSN will not happen in mere chlorobenzene. Although I have shown you the mechanism to explain, but it does not happen. Here the mechanism is the opposite, Cine substitution. Why ARSN doesn't happen in ordinary chlorobenzene? I have explained 2 points for you to answer in NCRT, in CBSE board examination. But my question is, what structural modification in chlorobenzene will make chlorobenzene, and that means that modified chlorobenzene a fit candidate to undergo ARSN. ARSN is addition followed by elimination type of substitution. Shruti, Shreya?
So, by adding group, another group,
Which group?
uh,
Yes. Which group?
so nitro group.
In general, which group?
So, deactivating group. Nine.
Precisely EWG. EWG, electron withdrawing group, as you also said, deactivating group, like nitro, like cyanide, like aldehyde, like carboxylic acid, like sulfonic acid. When there is you should have answered minus R groups or minus M. M is a word which is an old word which is used in benzene chemistry, aromatic chemistry, mesomeric, because resonance is also called mesomerism. So resonance effect is called also mesomeric effect. So minus R is also called minus M. But I find in many textbooks, the M word, mesomeric effect word, M word is missing. Only they are writing R, minus R groups. So in the presence of Miss Tripathi, in presence of any minus R group like nitro. For example, nitro, as the sisters have rightly told, nitro. What will happen? Nitro will withdraw the electron towards itself very profoundly and produce plus delta character in the orthopara positions. the one which was deactivating for ARSE will be activating for ARSN. Nitro, cyano, sulfonic acid and aldehyde, they were deactivators. मेटा डायरेक्टर्स छोड़ो, जाना है इलेक्ट्रोफाइल को, मेटा पोजीशन को, जो जाएगा ही जाएगा, लेकिन स्लोली जाएगा. लेकिन इधर ARSN के लिए अपोजिट, द सेम माइनस आर ग्रुप will make the benzene electron deficient, particularly in the orthopara position. So my second question will now to Samidha, if not then the sisters, is at what position with respect to the chloro group? In fact, that chloro will become the chloride leaving group. With what position with respect to the chloro group that we will keep the nitro group or any such minus R group, so that the ARSN will be taking place. Miss Samidha, I am not calling you by my font name, because this is a public record that we are making. Yes, Miss Sisters. You know,
Sir, ortho.
only ortho.
Orthopara.
Yes. Who told? Who
Sir,
told?
Sir Shreya.
Shreya. Yes, Amida. If that nitro group is only present in ortho or para or both positions, not meta, then only if you draw the resonance structures of such nitro in the para position or ortho position, then you find plus delta ortho to that nitro. And if chlorine is there at the ortho position, the plus delta will be in the carbon, ipso carbon with respect to chlorine. Then the the nucleophilicity of that carbon carrying chlorine will be enhanced, because that clearly will be possessing plus delta. But if nitro group is in the meta position with respect to chloro, then the resonance structures for nitro will be having ortho and meta, plus delta. So that will bypass the ipso carbon of chlorine. So the nucleophilicity of the carbon where the attack will happen will not be there. Therefore, the precondition to visualize the ARSN or to have ARSN, and there are umpteen number of proofs to corroborate that here the mechanism is going on is ARSN. Here the mechanism is SINE, SINE. So the conditions for ARSN minus R group or groups to be there in ortho para positions with respect to the halo group. Now I am showing you, supposing you have chlorine here and you have a nitro group here, so that the resonance structures of this nitro will produce plus delta and plus delta here. This makes nucleophilic center where the nucleophile will come, but I'm not writing the two steps. You will be asking, Samida, then you have to take nitrochlorobenzene, not a chlorobenzene. मैं तो वही कह रहा हूं, क्लोरोबेंजीन में ARSN नहीं होगा. मैंने कह दिया समझाने के लिए, लेकिन असल से नहीं होगा. रिगरस कंडीशन में होगा, लेकिन ये एसएन नहीं, ARSN नहीं है. ये उल्टा एलिमिनेशन फॉलोड बाय सब्स्टिट्यूशन टाइप ऑफ elimination followed by substitution, addition. Elimination followed by addition type of substitution called sign substitution will happen. So then the nucleophile, supposing you give the same KOH with, conditions will be, at about 100 degrees Celsius, without, that was needing concentrated KOH. I have not written. Very, very vigorous condition. Here, simply 1 molar solution will do the job at 100 degree. So the conditions are reduced, and this is ArSN, and the product will be this paranitrophenol. But if you take and two nitro, one in ortho, one in meta, one in para. There are two nitro. So the electron withdrawing effect will be so profound, plus delta plus delta. I mean, you will be so profound. This electron density will be so deficient here. Then the nucleophile, same KOH will be 0.001 molar. You will be doing that at 40 degree Celsius. You will be getting the corresponding phenol. What is the name of this? This is 2,4-dinitrophenol. Phenol is the original compound, phenol. So this 2,4-dinitrophenol will be produced very easily. And interestingly, if you have 3 nitro, 2 in the 2 ortho and 1 in the para position, then you will simply throw water. You need not have to take alkali. Simply throw water at the same room temperature. 40 or room temperature. You can just mildly warm it. You will find it will go, and this water is the nucleophile, then deprotonation will happen. You will get what we call picric acid. 2,4,6 trinitrophenol is its very popular name, but actually the IUPAC recommended name is not 2,4,6 trinitrophenol. Oh, yes. I'm so sorry. I confused about toluene. Since methyl or alkyl group is a type A group, doesn't have any priority. So the T and T here, I remind you, this has to be 2,4,6 trinitrophenol. This has to be one. This is a type C group. 2, 3, 4, 5, 6. 2,4,6 trinitrophenol, or very fondly called picric acid. But just for showing you how the same, supposing you have 2,4,6 trinitrotoluene or TNT, as it is popularly called, but the IUPAC is not TNT, trinitrophenol. Because here nitro, methyl, both are type A groups. They do not have any functional group priority. So you have to start from here. 1, 2, 3, 4, 5, 6. So not 1. I'm so sorry. That will be the number. The lower set of Locant's rule will not be valid. Start from here. 1, 2, 3, 4, 5, 6. This will be really called 2-methyl. M comes first. Then 1,3,5-trinitrobenzene. As you know, this is the IUPAC recommend. This is called PIN, preferred IUPAC name. But popular name is TNT. But for phenol, popular as well as IUPAC is 2,4,6 trinitrophenol, whose commercial name is picric acid. Okay. I have already told you the mechanism. ArSN consisting of arenide ion, resonance stabilized arenide ion, and in the second step, the halide ion goes. And now I have told you why. Because the answer is the question I have put, conditions I have put, but I didn't explain. Explanation is why? Because the presence of minus R group like nitro, CN, like COH, etc. in the orthopara position will produce plus delta charge on the ipso carbon with respect to ipso carbon with respect to chloro group. Hence, the nucleophilicity of that carbon will be enhanced. Although in general, benzene ring has electron cloud and it is not, it is itself a nucleophile. But once there is a nitro group which will take away most of the electron density towards themselves, towards itself, then it will produce a distinct plus delta at the orthopara position with respect to nitro, and therefore it will be producing plus delta at the ipso carbon with respect to chlorine. So hence the nucleophilicity of the ipso carbon to which the nucleophile will attack will be greatly enhanced. That is the answer you will give. That's it. Then before I enter into the classical preparation and properties, then I would like to tell you the other mechanism. The elimination followed by elimination is followed by is not written. Elimination followed by addition. Type of substitution. That is addition followed by elimination. This is opposite. This is called Cine substitution. And that happens through the benzyne intermediate, a very unstable benzyne intermediate. I'll show you. First, where it happens. It happens in chlorobenzene itself. I'll prove it. And particularly when you take a strong base and strong nucleophile like KNS2, where the amide ion is the nucleophile in presence of liquid ammonia solvent, then interestingly, interestingly, you get two products. One is the normal product where the leaving group is there, NH2, and one is the Cine product. Displaced, NH2 will be here. You will say, how will you know? How will you know that you will be getting two products? There is one position displaced. That can be known if you put supposing you have, better I show you a concrete example. Katidio, just got it. I'll put a methyl group here. And here I will put the leaving group. I'm taking 1-chloro 2-methyl benzene or orthochlorotoluene I'm taking. Then you will find that you are getting two distinct products. One is the normal product where the leaving group was there. There the new nucleophile will join. And the other one is here. Oh, sorry. One place displaced. So you get a mixture of normal product and this is the Cine substituted product, which is the nucleophile attacks both the position, both at the position where leaving group is there and also the position one place also the adjacent position. I'm saying adjacent. That means one position displaced, adjacent position. So how it is happening? You are having chloro here and you are getting You are taking a strong nucleophile, a strong base, amide ion, that should have given you one product. You are getting two products because we are having a different mechanism. I am showing you this mechanism where
Sir,
yeah,
sir, last sentence টা টিকে দেখাইবে কি?
लेकिन no, nucleophile attacks both at the position where leaving group is there and also the adjacent position, the Paco position. लेकिन लो.
Yes, sir.
Now see, supposing methyl group is there and here is the chlorine and I put the alternate double bonds like this, then I show you first elimination. Here, the strong base amide ion will be responsible to carry out beta elimination in two steps. First, this H. There is a double bond, pi bond here, but there will be a negative charge here. And then this will come here and Cl minus will go. So ultimately, of course, methyl is the host group is already there. Now see, you are getting a peculiar intermediate. We are having a triple bond. It's extremely unstable because it will make this hybridization from sp2 to sp, and that will be highly strained and that will burst out. And it happens. It's very, very unstable intermediate, but it does happen. This intermediate is called benzyne, benzyne intermediate. So the beta elimination happens in two steps by the strong base NH2 minus, and you get a benzyne intermediate. Now the benzyne intermediate has two ways to be attacked. Now ammonia is there. Ammonia abundantly as solvent is there, and amide ion, whatever amide ion was there, they have been used up forming, in the beta elimination, they have been used up in the beta elimination. So all are ammonia. So the ammonia can attack here in the normal position so that this pi bond, one of the pi bonds will polarize in the opposite side so that you will get the normal, then it will be, say, double bond, triple bond will be converted to double bond, and this will be NS3 plus. Because ammonia will lone pair will attack, so it is NS3 plus. Right? But the other possibility may not be as much possible, or the probability may not be as same, but maybe different. It can attack in the other side. So there is equal or maybe some appreciable chance of having the nucleophile attacking the benzyne in the adjacent position and to give you this. And now I have not shown you the minus sign here. I forgot to give you a minus sign here because it is polarized here. And now also I am showing a minus sign here. So you are getting both, maybe in unequal proportions, but you get both attacks. That is why you get a normal product as well as a product which is one place displaced adjacent product. Now, so proton rearrangement. So this is, we can write NH2H. So this abstracts a proton and neutralizes the charge. So you get the normal product. This is orthomethyl aniline or 2-methyl aniline. So the normal product. And here also you can just write down in place of NH3, you can write NH2H. And this, oh, I'm so sorry. This minus will abstract a proton and this plus charge will be neutralized to give you the sign product or the substitute, product which is the nucleophile is attached to one place adjacent position with respect to the living group. So you get this plus this. But now the question is which is major, which is minor, that will be decided by the I effect, only I effect. I will tell you why R effect is not used here. So since methyl is a plus I group, you have to consider, what happened to this one? লিভিগলা କେମିତି ଗୋଟେ ତମେ ଲେଖିଥିଲ? ଆରେ ଡ୍ର କରିଥିଲ ନା ନାଇଁ?
Yes, sir.
ଖାଲି ଶୁଣୁଛ ଭାଗବତ ଶୁଣିଲା ଭଳିଆ? କେମିତି ଲିଭିଗଲା? ଆଉ ଥରେ ଦେଖେଇବି, ଲେଖି ସାରିଲଣି? Shami?
Yes, sir.
Yes, sir.
Only the I effect will decide which is major, which is minor. Now see, between these carbanions, which is more stable carbanion? The negative charge, if it remains closer to a plus I group, this is a plus I group, then it will be destabilized. So this carbanion is more unstable compared to this carbanion because this is closer to a plus I group, which will, instead of delocalization, it will localize the negative charge and make it unstable. So the farther the negative charge from a plus I group, relatively it is more stable. This is more stable. Comparatively, this is less stable. Only you have to explain through minus I effect or plus I. Here it is plus I. I'll give another example showing a minus I effect, like OCS3. And what happens? You get this is the major. The normal product is major. This is minor. Supposing this is 70, this is 30. But why this 30? Appreciable amount of the displaced product is found. That the scientist sign was really astonished. Then he started, establishing the mechanism. Why it is happening? No, ArSN is not happening. It is something different. So he trapped the benzene intermediate. Benzene is an intermediate. It's not a transition state. He trapped it by putting some other addendum by cycloaddition reaction. He trapped it, proved that yes, it is going via benzene. So a new mechanism was propounded, is elimination followed by addition kind of. Now see why it is called elimination. First beta elimination happens to form benzene. Then ammonia is added. So this is elimination followed by addition. But in the ArSN that we studied, the mechanism that we studied, first addition of nucleophile, then elimination of the living group. So this is addition followed by elimination. But the other one is elimination followed by addition, the opposite. When it happens, when there is a strong base like amide ion, the amide ion is there. Mostly you will find amide ion, even OH minus ion, not having a minus R group. There is a minus R group like nitro or sulfonic acid, then it is ArSN. If it is a plus I or minus I group, interestingly, I will give you another example where three products are obtained. Supposing you are having methyl here and chlorine here, and you are carrying out KNS2 with liquid ammonia. You are getting, a mixture of three products, normal product and two sine product. This is adjacent position, this is adjacent position. Who can tell me why three products we are getting? In unequal yields, usually the normal product predominates because it happens in both the I'll tell you the positions. I mean here. So this is the position where the living group was there. So this is the normal product. But these are the sign substituted product, these two. Why you are getting three products here? Who can tell me?
Sir, sir, CH3 sir, activating group तो ସେଥିପାଇଁ para ଆଉ ortho position ରେ NH2 ଟା ରହିବ।
No. Miss Misra and Miss Misra, you could not get it. Miss Tripathi? କାହିଁକି ତିନିଟା product ମିଳିଲା ଏଠି? And I am telling this is again sign substitution. Why? It means you are unable to think. Okay. Yes.
तो से Cl गले से कार्बन टा प्लस है जो तो
I have already shown you the mechanism. I have shown you the mechanism. I have shown you the elimination followed by addition type of mechanism. I have shown you. I am showing you once again. Now can you answer, Sutisreya? भोर आई गया अंधियारा, भोर आई गया अंधियारा, भोर आई गया अंधियारा, भोर आई गया अंधियारा. When I answer this, you will feel really, you will sigh away. ଲାଜ ଲାଗିବ ତୁମକୁ. ଲାଜରେ ତମେ ଇଏ ହେଇଯିବ, ମଉଳି ଯିବ. What you told plus I effect, ଏ plus I effect ରେ ଉଲ୍ଟା ArSN ହେଇପାରିବନି. ସିଏ ଭାବୁଥିଲେ କ'ଣ ସିଷ୍ଟର୍ସ, ଯେ ଯେହେତୁ ମାଇନସ୍ ଆର୍ ଗ୍ରୁପ ରହିଲେ ArSN ହେଇପାରୁଛି, ପ୍ଲସ୍ ଆର୍ ଗ୍ରୁପ ରହିଲେ ଆଉ ଗୋଟେ ନୂଆ ସାଇନ୍ ସବଷ୍ଟିଟ୍ୟୁସନ୍ ହେଇପାରିବ. ତା ପାଇଁ କୌଣସି ସାଇନ୍ ସବଷ୍ଟିଟ୍ୟୁସନ୍ ପାଇଁ ଏଲିମିନେସନ୍ ହେଉଛି ଆଗ. ଗୋଟେ ଷ୍ଟ୍ରଙ୍ଗ ବେସ୍ ଦରକାର, NH2 ମାଇନସ୍, and a presence of a group which is not minus R. ନାଇଟ୍ରୋ ସଲଫୋନିକ୍ ଏସିଡ୍ ଏଇଟା ନଥିବ. ଅନ୍ୟ ଯାହା ଥିବ ଲାଇକ୍ ପ୍ଲସ୍ ଆର୍ ଗ୍ରୁପ୍ ଥିବ, ପ୍ଲସ୍ ଆଇ ଗ୍ରୁପ୍ ଥିବ, ପ୍ଲସ୍ ଆର୍ ଗ୍ରୁପ୍ ଥିବ, ପ୍ଲସ୍ ଆଇ ଥିବ, ସେଇଟା ହେଲେ ଚଳିବ. ରିଜିନ୍ ହେଉଛି you will get two benzynes. ଏପଟ ହାଇଡ୍ରୋଜେନ୍ ଗଲେ ଏଠି ବେଞ୍ଜାଇନ୍ ହବ, ଏପଟ ହାଇଡ୍ରୋଜେନ୍ ଗଲେ ଏଠି ବେଞ୍ଜାଇନ୍ ହବ. So two benzyne intermediates are formed because ଏପଟେ ବି ବିଟା ହାଇଡ୍ରୋଜେନ୍ ଅଛି, ସେପଟେ ବି ବିଟା ହାଇଡ୍ରୋଜେନ୍ ଅଛି. ସେଥିପାଇଁ ଯେତେବେଳେ ନ୍ୟୁକ୍ଲିଓଫାଇଲ୍ ଆଟାକ୍ କରିବ, ଏଇଠି ଏଠି ଗୋଟେ ସାଇନ୍ ପ୍ରଡକ୍ଟ, ଗୋଟେ ନର୍ମାଲ ପ୍ରଡକ୍ଟ, ଏଇଟା ସାଇନ୍ ପ୍ରଡକ୍ଟ, ଏଇଟା ନର୍ମାଲ ପ୍ରଡକ୍ଟ. So normal product are two times alike. A benzyne re be normal product, A benzyne re be normal product. But sign product 80 gote, 80 gote. So in this case, normally you get usually you get the normal product as the dominant product. Sign product as less. You understood now, Miss Sisters?
Yes, sir.
How many benzynes will be formed in this case?
Sir, 2.
Because A hydrogen टा गले ମୁଁ ଦେଖେଇ ଦଉଛି, ଲିଭେଇ ଦେବି. ବେଞ୍ଜାଇନ୍ ଏଠି ହେଲା, ମୁଁ ମେକାନିଜମ୍ ଲେଖୁନି. ଆଉ ଏ ହାଇଡ୍ରୋଜେନଟା ଗଲେ ମାନେ ବାଇଗଣଟା ଏଠି ଲେଖିବି, ଏମିତି 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 କରିବି ଆଉ କ'ଣ. ଗଲେ ଏଟା ଏଠି ସିଙ୍ଗଲ ବଣ୍ଡ ଅଛି, ଏଠି ଡବଲ, ସେ କେସ୍ରେ ଏଠି ଡବଲ ବଣ୍ଡ କରିବି ଏଠି ଆଉ କ'ଣ. ଏଇଠି ଗଲେ ଟ୍ରିପଲ ବଣ୍ଡଟା ଏଠି ପଡ଼ିବ. So there are two benzyne formation here, so that you get three products. Interestingly, ଆଉ ଗୋଟେ ଏକ୍ସାମ୍ପଲ ଦଉଛି, तर OCH3 group ଅଛି. Why? This is a plus R group, but you cannot use plus R group. Plus R will be happening, but that will, not allow the ArSN to happen. ArSN minus R group here hobo. Since it is a different opposite mechanism, ଏଠି କେବଳ minus I effect will be considered to explain which one is the major product, which one is the minor product. Plus R effect is not. I'll give you further explanation on that. Supposing chlorine is here, you are carrying out same KNS2 and liquid ammonia, you will get the same two products. One is the normal product, which is 2-methoxyaniline and 3-methoxyaniline. In this case, the sign product is major, this is minor. Why? Because if you draw the mechanism, I'm just showing you the comparison. In mechanism, you will compare between, OCH3 here with a negative charge here, and compare and here NH3 plus, and the other one already attacked. Benzene has been already attacked, and triple bond has been already converted to a double bond. I wrote it wrongly. So the other one is attacking at the normal product NH3 plus, and minus will be creating here. Now to compare between the stability, compare between the two carbanions, which is comparatively more stable, by using minus I effect, that since it is closer to a minus I group, and hence it is more stable. And this is less stable. The negative charge is farther away from the minus I group. This is less stable. So the ultimate product after proton transfer, here there was, there is no proton, here is extra proton. So this will abstract a proton and this will neutralize. So this product will be the major product, the sign product here. And the normal product will be minor. This is major. We will not use plus R effect to show that there is a plus delta character here. Minus delta character here, minus delta character here. We are not doing electrophilic substitution. We are doing nucleophilic substitution. A nucleophile has already attacked. Ammonia has already attacked in the second state after elimination, after forming benzene. The nucleophile ammonia has already attacked. So here the plus R effect will be redundant. The minus I effect will only explain which is relatively more populous, more abundant compared to the other one. You understood? Miss sisters?
Yes, sir.
Yes,
Samida?
yes, sir.
Now, interestingly, now see how you prove that in mere chlorobenzene with the KOH that you are using and vigorous conditions are using, no doubt, you are getting phenol. How? Because sign substitution is happening. I am showing you in haste. In one step, I am showing you the benzene formation. And let us take a labeled chlorobenzene where this carbon, ipso carbon, is C14. We label in the laboratory, we can label a particular carbon with 100% C14. This is 100% C14. Others are normal C12. This is called a labeled chlorobenzene. C14 labeled. And when that happens, you are really getting, benzene here. There is nothing. But one is labeled, this is non-labeled, star, sorry. So when OH minus will attack this as well as this, so you get one product, no doubt, but 50% will be the phenol, which is in which the OH is connected to the labeled carbon, and 50% same phenol, it is connected to this position. Here, this is phenol. The labeled carbon is not bearing any OH group. Even if one product is formed, but 50% phenol will be that in which OH is bonded to the labeled carbon, another 50% one place displaced, the adjacent position. It clearly proves that even if it is chlorobenzene, ARSN is not happening, a rather sign substitution is happening. ମୁଁ କିନ୍ତୁ unfortunately explain କଲି ତୁମକୁ କ'ଣ ନା using chlorobenzene, which I should not have. This is sign substitution. Now, before we end, I will really tell you the mechanism, ArSN mechanism, which is really happening. Chloro is there and some nitro group. I'm showing one nitro. And clockwise rotation kariya. सेमती किसी माने नहीं, you will show clockwise rotation. And now, in the first, which is slow, in the first step, the nucleophile attacks because there is a plus delta character here. Mechanism likely plus delta likhi. And this will come here to form a arenide ion and show the resonance structure. Then you show another resonance structure. You'll find here there are 4 resonance structures here, not one. I'm sorry. It asla mane eta polarize hegeretic pole asib. But nitro group is already there. It is there. And here is the charge. And now it will enter into the benzene ring, sorry, into the nitro group to have the 4th resonance structure. ଅର୍ଥ ପାରାରେ ରହିଲେ ହିଁ ସେ ଭିତରକୁ ପଶି ପାରିବ। ଏମିତି ତ ଆମେ ବୁଝେଇଲା ବେଳକୁ କାହିଁକି ନ୍ୟୁକ୍ଲିଓଫିଲିସିଟି ଆଟ୍ ଦି ଇପ୍ସୋ କାର୍ବନ ବିକମ୍ସ ଏନହାନ୍ସଡ୍ ସେଟା ତ ବୁଝେଇଦେଲୁ, କ୍ୱାଲିଟେଟିଭଲି ଆମେ କହିଦେଲୁ ହବ, କିନ୍ତୁ ହେଲା ବେଳେ ମେକାନିଜମରେ we have to show that the arenide ion is more stable because of more number of resonance structures so that it will form. ଏଇଟା ତ ଡେଟିଭ ବଣ୍ଡଟା ପ୍ଲସ୍ ମାଇନସ୍ ସବୁବେଳେ ହମେଶା it will remain. So you get an additional, and finally what happened, the 4th one will be, this will come here, this will, we were going clockwise, so this will come here and this will come here. So both the ortho positions will be having negative charge in 2 resonance structures, and para will be 1, and another one in which oxygen will be a double minus, and the new minus is the formation of that resonance structure. These plus minus, they are formal charges for the dative bond. So you are now getting minus charge here, and this pi bond has polarized. This is a pi bond polarized, and double bond has come, pi bond has come here, and nitro group is as usual double bond and plus minus, and we have Cl and Nu. So there are 4, 1, 2, 3, 4 C. The original one, 2, and this one is the new one, where nitro group is taking part in resonance. It is withdrawing the para lone pair towards the other oxygen and giving another resonance structure. So more stable arenide ion having 4 resonance structures. And then in the second step, that is nothing in the second step, which is fast. And this comes here, this goes, and you get. ମୁଁ ଏଠି ଆଳୁ କରିଦେଲି because already our mechanism ସରିଗଲାଣି. So Nu is permanently attached here in the place of the living group, and already existing group as NO2. You got it?
Yes, sir.
And if there will be one more nitro in the ortho position, you'll be, instead of 4, we have 5. It will go into that this nitro and also this nitro 5. If you have another nitro in the other ortho, you'll have got 6 resonance structures. So more is the number of nitro group in the ortho para positions. If it is in a meta, it will bypass, it will not enter. You will do and clarify, convince yourself. If it is only in the orthopara position, then you get more number of resonance structures. That is why these will be ARSN, not mere benzene, mere chlorobenzene रे मुझे दिखाई दिली, that it is not really happening. Let me now write with a conviction that this is not really happening. Simply, I explained the 2 steps by taking chlorobenzene, but it will not happen. This will go via Cine substitution mechanism that I have already explained. Now, I will like to close the session, but still some more time is required for the study of the preparation of chlorobenzene and other halobenzenes and their properties. Either we can see it once more if you like, but I don't have any video recording. I will upload this video. This video is not weird. The morning recording I did record, but that was a weird kind of recording. So I even didn't want it. I was always making public video for some reason. Reason being, at least 1 or 2 guys, maybe 1, 2, 3 अगर benefit इनको मिलता है तो मुझे सुकून मिलेगा. I am not after the number 20. That time was there when I was teaching hundreds of students and they're flocking to my house, and people were counting how many students Sari is teaching. So that time is no more there. I am only interested of in kind of student like you, all 3 of you, and Rudra. So Sami, you have to decide if, and Nani, Shruti Nani and Shreya Nani, you have to decide. Tomorrow morning I cannot give you time because it is class 11 time, and in the afternoon, if you are free, all of you 3, then I am really interested to make a video on the other part. Now, ebe kordoba kujo. Are you free? Shruti Shreya?
Yes, sir.
Another half an hour tome bas paribo?
Yes, sir.
Sami?
Yes, sir.
Okay, Sardava. ଆଉ ମୁଁ ଲେଖିବିନି. I won't write anything. But only thing I will go for half a minute to answer the call of nature. Okay. Now I will show you these slides. Preparation of halobenzene, particularly chloro and bromobenzene, can be done by halogenation, that is ARSC from benzene. If it is benzene, it will give chlorobenzene or bromobenzene. You have to take halogen carrier, FeCl3 or FeBr3 as the case may be, or simply iron metal if excess of halogen is there. And you know, by the reaction of X2 with FeX3, you will get the electrophile X plus chloronium ion or bromonium ion plus FeX4 minus. So this will attack to the benzene ring, that is ARSC. And if there is another host group, then it is OP director. You get a mixture of orthopara. The same mechanism, because you know the ortho position and para position is electron rich. The minus delta is there, so electrophile will love to attack at that position with greater rate because it is also an activator. Now, iodobenzene is prepared in a different way, not iodine with API3. You have to take iodine with some nitric acid or cupric chloride. Some oxidant is necessary. So what happens in the presence of that oxidant Cu2 plus or NO3 minus, you get I plus ion, iodonium ion, and that is the electrophile for the ARSC. And you can also take a very interesting compound, iodine monochloride, because in halogen chemistry we will study that halogens can form interhalogen compound, ICl, ICl3, IF3, IF7. So ICl if you take, then since iodine is has a greater size, chlorine is more electronegative, so the heterolytic cleavage will occur towards chlorine, so I plus will be formed, and same way ARSC will happen to produce iodobenzene. Now see, this is the commercial method of preparation of chlorobenzene, where you take benzene with HCl and bubble oxygen gas with pressure and the presence of cupric chloride catalyst. So you get chlorobenzene. This is simply a catalyst and water. Chloro will join here, and this H coming from one H coming from benzene and the other H here, and half oxygen, that will give you water. This I have not shown you the mechanism, but it has to be ARSC. I have not shown you the mechanism. And the other way is through benzene diazonium chloride, which we shall study in details in the chemistry of amines. Aromatic amines are called, that is aniline. But I will tell you that here how we prepare that through Sandmeyer's reaction. I'm writing here preparation of chlorobenzene or bromobenzene from aniline via benzene diazonium chloride. It's shortly called BDC. Now we will again know in details in our amine chemistry, but it's not difficult. Supposing you have amine and then you treat it with NaNO2 and HCl at 0 degree Celsius, which will produce HNO2, nitrous acid, and that will react with this. I'm showing in a very crude way. Nitrous acid is like this. So you get a kind of compound which is very interesting. N double bond N and Cl. Here one water goes, here one water goes. SC because HCl is there. But it has got another stable structure. this lone pair will come here and this chloride ion will go. So a more stable structure will be a triple bond with plus charge here, lone pair here, and chloride ion is outside. So this is called BDC. Benzene, the same. These two are in equilibrium. Uh, it's not resonance. This is a non-ionic structure. This is ionic structure. This is more stable ionic structure. Sometimes the reaction, as we shall study then, sometimes the reaction happens through non-ionic structure, and most of the substitution reactions, we are not studying the mechanism here, or BDC takes place from the ionic structures N triple bond N plus here and minus. Chloride ion is away. It's already gone. Now the living group is nitrogen gas. So here you have to perform Sandmeyer's reaction. If you take cuprous chloride, you get chloride ion will go and carry out SN1. Here SN1 happens. Nitrogen will go. If this bond will break, nitrogen will go and chlorine will come. If it is CuBr, then instead of chlorobenzene, this will give you bromobenzene. And if it will be CuC and cuprocyanide, instead of bromochloro, you will get cyanobenzene called benzonitrile. Benzonitrile. So these three, these are called Sandmeyer's reaction. Sandmeyer reaction is a reaction of BDC, not a reaction of aniline. We started from aniline, but it is the reaction of BDC. So we are interested in chloro and bromo, not cyano now. But we studied the entire Sandmeyer's reaction from BDC. So in the NCERT book, you are told to write only CuCl, CuBr, CuCl. But in many other literature, you will find CuCl plus HCl, CuBr plus HBr, CuCl plus HCl. So this will be a better, more effective Sandmeyer reaction than not taking the corresponding hydrides, HCl, HBr, HCl. So I'm writing in bracket. You will not find in NCERT book any combination of CuCl with HCl or CuBr with HBr or CuCl with HCl. Simply only one compound. So this is the way. And I'm coming back to the slide. You can take any substituted benzene like alkyl benzene. Since this alkyl group is OP director, you get a mixture of ortho and para product. You already know. It's interesting is the properties. Chlorobenzene is a colorless and flammable aromatic liquid. Boiling point 132 is it catches fire. It's flammable. Fluorobenzene is colorless liquid, but bromo and iodobenzenes are colorless if freshly prepared, but becomes pale yellow in the AZ sample because of photochemical reaction. Light breaks down the bond and produces iodine and chlorine in small amounts that makes it pale yellow. And the boiling point and melting point, they are very interesting. Ortho, boiling point wise, ortho is the highest and meta is the lowest. And always para is less than ortho in boiling point. But the reverse is the trend in melting point. The highest is para melting point. Of course, the lowest is always meta in both boiling and melting. But between ortho and para, you will find para is most in melting than ortho. But opposite happens. Ortho is has more boiling point than para. But in both the cases of boiling point and melting point, the meta is the minimum. Why? Because in the solid state where the molecules need to pack closely to form the crystal, the packing becomes more if this is a symmetrical structure and this is a non-polar structure. The two vectors will cancel out or minimize. Here it is the net dipole moment is 0, but in the para, so there will be a symmetrical structure and the packing will be very, very efficient. So melting point is 323 vis-a-vis, where here the packing will be very, very loose. But the most loose is the meta. But in case of boiling point, the van der Waals force will be more. More is the dissymmetry, more is the polarity. So their contact area will be more, and therefore the van der Waals force. Packing is not an important. They are mobile. So the van der Waals forces is maximum for ortho. But here in melting, the van der Waals forces is maximum in para. Therefore, para boiling point is less than ortho. But in melting point, the para has a higher melting point than ortho. In both the cases, the meta has the lowest value both in melting and boiling. We have already seen, I have written why in chlorobenzene ArSN is difficult. I have told you sp2 hybridized, and here I have given you the bond length, which is inversely related to bond strength. In chlorobenzene, since it's sp2, the bond length is 169 picometer, while in haloalkanes it is 177 because of sp3. So this bond is strong, and moreover benzene itself is a nucleophile, and SN1 is also difficult because phenyl carbocation is unstable. But you may ask me again, you are telling in BDC why it is SN1. That is the only choice available. Because N2 is a very good living group. Livability of nitrogen gas is so profound that ARSN happens in BDC. But usually it doesn't happen in chlorobenzene. So SN1 is ruled out. So this reason I have not written, but for your examination, these 2 points you have to mention. Then activation. How the ARSN reaction is activated by the placement. This activation word I didn't write, but it is really activating for the ARSN by placing a minus R group at the orthopara position. That I have shown you. Chlorobenzene I have explained, but this doesn't happen. It happens in the other way. But ARSN is called addition elimination type of substitution, but this is not a reality, this explanation. But when a nitro group is there, you have 4 resonance structures. I am showing you the resonance structures not in the mechanism, but showing how the nucleophilicity enhances. The plus delta character in the ipso carbon is more, the nucleophilicity of that carbon increases, the nucleophile attacks. But this is not the mechanism. This is an explanation to show why the ARSN becomes increasingly easier with a minus R group in the orthopara position. So this you already know. And here is the mechanism. The arenide ion has more number of resonance structures, and then I have already explained this. And see, the data गुड़ाक ठीक देई नथिली correction कर दबो 350 degree Celsius 150 concentrated NOH you get phenol, but ARSN doesn't happen here. It is sign substitution. And if there is one nitro group, ARSN starts. The conditions are less vigorous. Instead of 150, move with 100 na kon lekithili 150, and it is concentrated is 1m. Eta ठीक lekithili. So the conditions are less vigorous. And ARSN starts here because there is a nitro group. If there are 2 nitro group, the conditions are still less severe. 0.001 m and 100 degree. And if it is trinitro, then only water 40 degree will make it picric acid. 2,4,6 trinitrophenol. I have already explained this, need not write. And you can get the aniline. This is a property of chlorobenzene. Chlorobenzene doesn't show good ARSN. So whatever happens, it is through ARSE. That will be studied by taking a labeled chlorobenzene. And I have not given you the mechanism here, but you can get aniline with much difficulty, with so much of catalyst, so much of pressure, so much of catalyst, ammonium molybdate, phosphoric acid, cupric chloride, all. It's very difficult. ARSN is very difficult in mere chlorobenzene, unless there is a minus R group. You can also get cyanobenzene with cuprous cyanide. The same manner, it's difficult, but it is possible. And then we are now studying the ARSC of chlorobenzene, where chloro will be hosting, it will remain. Other electrophile will join. This is the ARSC of chlorobenzene, where chloride is not the living group, it is a host group. If you make further chlorination, since it is OP director, you get a mixture of ortho and para. And if you carry out Friedel-Crafts reaction, you'll get a mixture of ortho and para. If you take a Friedel-Crafts acylation, you get para major because acetyl carbocation, acetyl group is bulky, chlorine is also equally bulky, not equally, but bulky. So para is the dominant product, 90%. So here also para is the major product because chloro is not like fluorine. Now, if you carry out nitration, you again get orthometa. Orthopara. In all the cases, orthopara. Sulfuration, orthopara, but para is major because sulfuric acid, who can tell me what is the electrophile in sulfonation? Yes. Just like in chlorination, Cl plus, in nitration, NO2 plus, in alkylation it is R plus, in acylation it RCO plus. And what is the nucleophile in sulfonation? Sami?
Sir, HSO3 minus.
Huh? Huh?
Sir, HSO3 minus.
Are you kidding me? Electrophiles are positive. We are talking of electrophilic. We are not studying nucleophilic. We are studying electrophilic, where chlorine that is a host group, and other electrophile will join in the orthopara position. So the electrophile cannot be negative. Negative ions are nucleophiles. Yes, Shruti, Shreya. ସମିଲାନି ତମେ ଭୁଲି ଯାଇଛ ମୁଁ ଯଦି ମନେ ପକେଇଦେବି you will be cursing yourself. ଆମେ ଆରିନ୍ସ ପଢିଲା ବେଳେ all types of ARSC ର କଣ କଣ ଇଲେକ୍ଟ୍ରୋଫାଇଲ କିଏ ଆମେ ପଢିଛେ ଶ୍ରୁତି ମନେ ପଡିଲା ସେୟା ମନେ ପଡିଲା ନା ନାହିଁ ସେ ଦିଟା SO3 neutral SO3 and SO3H plus ମନେ ପଡିଲା ନାନି public video ମନେ ପଡିଲା not minus but what
Plus.
plus the fuming sulfuric acid H2SO4 will break down into two molecules will have a disproportionation. One will be SO3H plus, the other one is HSO4 minus. The SO3H plus is a sulfur nucleophile. Sulfur electrophile, not a nucleophile, sulfur. So sulfur will be attacking, that carries the plus charge, and not attacking, it will be attacked by the pi bond. And SO3 neutral, all are double bonds. There is no lone pairs. It cannot be a nucleophile. All are double bonds. So the benzene attacks, polarizes one bond. We have done extensively the mechanism of ARSC. Manipula? Samidhan?
Yes, sir.
And here you get a small amount of, small magnitude of kinetic isotope effect in sulfonation. You get KH by KD is approximately equal to 2. But in all other ARSC, it will be 1. That means no kinetic isotope effect. Okay. Sign substitution already we have done. See, it a para-chlorotoluene. Here is this is the host group, and this will leave, forming a benzene. Benzene, epote jo benzene, sepote sei benzene. So only one benzene will be formed here. So you get two products. One is the normal product, the no sign product. This is equimolar, but here, when there is a minus I group here, although OCH3 is a plus R group, but we are not considering any ARSC. The sign substitution plus R effect is not considered. Minus I effect is considered. I have already explained you the major product, but here I give you the data that the exclusive abundant, 100% product nearly is the sign product. You will be astonished. Sign was himself astonished when he took, 1-chloro, 2-methoxybenzene and carried out, treated with sodamide and or potassiumide. Sodamide is best choice. Move into potassiumide, but make it sodamide with liquid ammonia. you are substituting chloride with amide. I mean, you are getting no product where the amide NH2 group, amino group is attached to. The nucleophile is called amide ion, but actually amide ion is not the nucleophile. Ammonia is the nucleophile because amide ion has done the elimination job, forming triple bond formation, that is benzene, right? So we have done this, and there are three products. Because there are two benzenes from here that we already know. This is an important one for your NCERT. Urge phytic. Only urge is alkyl halide. But if you mix chlorobenzene with alkyl halide and sodium ether, then you will get alkyl benzene. This is called urge phytic. Only phytic is between two chlorobenzene. If you take only chlorobenzene and add sodium in ether, then you get two benzene rings fused, not fused, will be joined with a single bond. This is called biphenyl. So this is urge phytic and this is phytic. And finally, we can study about the preparation and properties of allyl, vinyl, and benzyl halides. I'll take only 5 minutes. My tea is getting cold. Give me 1 minute. You know, allylic, na, video. ଖାଉଛି ଏଠି ପିମ୍ପୁଡ଼ି ଯେମିତି ହଉଛି ବେଳେ ବେଳେ ମୋ ଅବସ୍ଥା ଖରାପ ହେଇଯାଉଛି ପଡୁଛି କିବୋର୍ଡରେ I'm sorry, girls. It's very discourteous. And viewers who will be watching later. Now here is the allylic chlorination and bromination. We take NCS or NBS for bromination. N-bromosuccinimide, N-chlorosuccinimide, or its alternative is third butyl hypochlorite, where it will attack at the allylic position. Here is the allylic position. So you get allyl chloride or allyl bromide. And if there is no allylic position, take only ethylene, you get vinyl chloride. This is high temperature chlorination. All these are free radical mechanism substitution. And if you take controlled addition of acetylene with HCl in presence of mercuric salt, you get only one HCl added to give vinyl chloride. Grignard reagent can be prepared from chlorobenzene with same way magnesium in ether solvent or tetrahydropuran, which is an aromatic ether solvent, to get phenyl magnesium halide, which is an aromatic Grignard reagent. If you are taking a dichlorobenzene, 1,2-dichlorobenzene, and simply heating high temperature, then one HCl will be eliminated here at high temperature and high pressure, not very high pressure. You get vinyl chloride. So there are two ways of getting vinyl chloride: with a substitution reaction from ethylene and from elimination reaction of 1,2-dichloroethane. Only single elimination occurs to give vinyl chloride. And now from toluene, you can carry out halogenation in presence of sunlight. Chlorine, 1 mole will give you benzyl chloride. This is what we call the side substitution. not the ring substitution, side substitution, which doesn't require FeCl3, simply light. If there is an alpha hydrogen, so it will be substituted by chlorine by free radical mechanism. Then the second mole of chlorine will make it benzal or benzylidene chloride. Third mole will give you benzotrichloride. So this, and the properties of these unusual kind of halides, allyl, vinyl and benzyl. This is allyl, this is vinyl, and this is benzyl. This one is benzyl. We are talking about these three. हमें extension कर देले, we control the substitution, the free radical substitution to the benzyl chloride stage. And this allyl chloride we know, and vinyl chloride. तारो properties हमें देखो छे. Allyl chloride is very prone to SN1 reaction because the allyl carbocation is very strong. It's very stable, not very, very stable, stable. So it will favor SN1 and sometimes SN1 dash. Supposing here is one methyl group, then this carbocation will be rearranged to give you this carbocation, which is secondary allyl carbocation, which is more stable than the primary allyl carbocation. So chlorine can join here. OH minus can join here. So that is the internal rearranged product. So this is same. It's called SN1 dash. So you can also carry out, when there is a double bond, you can carry out polymerization with some peroxide catalyst to bring about this vinyl chloride will give you PVC, polyvinyl chloride, which is a plastic. Benzyl chloride is so very prone to hydrolysis. Simply you add water, because benzyl carbocation is so stable that you do not need NaOH. Simply water, you get benzyl alcohol, SN1. If you take it out additional, buy one, get one free. If you take benzyl chloride, then add water, you get, geminal diol is unstable, a molecule of water is eliminated immediately, you get benzaldehyde. If you take benzotrichloride and add water, the geminal triol is also unstable. It eliminates readily a molecule of water to give you benzoic acid. And DDT is now outdated. It was a very, very powerful insecticide in early and the late 20th century. DDT is nothing but dichlorodiphenyl trichloroethane. Dichlorodiphenyl, trichloromethane. Ethane, I'm sorry, the two carbon atoms. So dichlorodiphenyl trichloroethane. How you prepare? Take 2 moles of chlorobenzene and 1 mole of chloral. This is trichloroacetaldehyde. CH3 has been converted to CCl3. We will know how chloral is obtained from acetaldehyde. 1 mole chloran and 2 mole chlorobenzene, they will immediately react. A para hydrogen theta, it O, Saligala, and the double bond is bifurcated into 2 single bonds. So this is nothing but DDT. And the actual good name is 2,2-bis dichloro, 2,2. Why 2,2? Because 1 is here, it contains 3 chlorine atoms, more substituents are there, 2 is here. So 2,2-bis, and each one is para-chloro or 4-chlorophenyl. So since it is a complex group, bis word is there, not di. Bis 4-chlorophenyl, then 1,1,1 trichloroethane, which is very fondly called dichlorodiphenyl trichloroethane, DDT. And this is very most important part for your examination is this one, silver nitrate test to distinguish between halides. You add silver nitrate solution, you get some precipitate. Silver nitrate will give you silver chloride white precipitate with chloro containing compounds, and bromo containing compounds will give you light yellow precipitate, and iodine containing compound you get a yellow precipitate, silver iodide, silver chloride, silver bromide. Silver chloride is white. And the reactivity order is 3 degree is greater than 2 degree halide, greater than 1 degree halide, because the carbocation stability goes in that order. And among iodide, bromide, chloride, iodide is most reactive, then bromide, then chloride, because the livability of the group is according to that order. Now, this is most important. Any tertiary halides, because tertiary carbocation is so stable. And among iodides, the livability of iodide ion is so high that even methyl iodide and ethyl iodide, and allyl carbocation is stable, and ethyl bromide. These four, all tertiary halides, methyl and ethyl iodides, all allyl halides, and ethyl bromide. These are the four categories of halides which readily forms precipitate at room temperature with silver nitrate. But others which have unstable carbocation, they give on heating. For example, 1 degree, 2 degree chlorides, even benzyl chloride give precipitate only on warming. Chlorobenzene, vinyl chloride, chloroform, iodoform, carbon tetrachloride, etc. They do not give any precipitate even on heating. They don't respond to silver nitrate test because the substitution reaction, the ArSN is difficult with chlorobenzene itself. So if it is a aromatic compound or even vinyl carbocation is not stable, and here it's not possible to substitute chloride by nitrate, because the one Cl minus will go, but the bond is so strong it won't go in this compound. So remember, these do not respond to silver nitrate test. So the mechanism is very simple. Any halide, silver plus and NO3 minus, this will act as electrophile to facilitate the heterolytic cleavage. Silver ion is the catalyst to facilitate the CX bond breaking to form a carbocation, maybe stable or maybe more stable or whatever. Then if there is ethanolic solution, then ethanolic solution of silver nitrate, then ethanol will act as but this X minus is gone and it has added with silver ion to form silver halide precipitate. This is grossly covalent. But what will be the fate of the carbocation? Because nitrate ion will not be joining, but the solvent will be carrying out solvolysis. If there is ethanolic silver nitrate, then ethanol will attack and the product ultimate after deprotonation will produce ether. If it is water, usually water is not taken because most of the organic halides, they are not soluble in water. They are soluble in ethanol. So the solvent chosen is ethanol. So ultimately one ether is produced, but this precipitate indicates the halobenzene. So this is the end of our program, and I will upload it soon, and I will make it public to at least to Prachi and also who could not attend today. Bye-bye.
Thank you, sir.
Thank you, sir.